Hi everyone, I'm Zhao Chen. I'm here for the tutorial deliver his talk. I'm happy to show the recent advance on the deep knowledge tracing based knowledge tracing models. Okay, this talk is divided for parts. In the first part, I will introduce the background and the history of the knowledge tracing, and then I will classify the basic model, and then I introduce some representative models. Then I will introduce the recent advance, and the last I will talk the application and the future research direction. Okay, now let's see the first part. We all know the one-on-one human tutors dramatically improve the education outcomes. And boom, in the 1984, hypothesis that the improvement can be 2 sigma. But we cannot to assign a teacher for each student because we are not so many teachers in here. Unfortunately, online learning can bring us many data sets. Here at least some common use data set in the KT. I think there's no teacher can read all the interaction in their life, but the computer can. So by combine the data and the AI and the machine learning, we can build an intelligent online tutoring system. We call that ITS. The core of ITS is how to assess the ability of students. Basically, there are 2 categories. The first one, we call that cognitive diagnosis. The input is the question with the response. And the output is the master level of each knowledge component. This model then consider the temperature dimension. The next one is the knowledge tracing. That will evaluate the ability development by time. Okay, now let us see the history of the assessment. In the early 20th century, the common use method, the classic metric theory, they use the paper score to assess learning ability. However, the score are sensitive to the test question factor. So in the 1950s, the attitude bounds theory was being proposed. They calculate the learning competencies with the undimensional competency values. And in the 2009, the DINA model was being proposed, and they use model the learning competency, use a multi-dimension. Upon knowledge tracing, in the 1994, Cobalt and Albert proposed a new task named knowledge tracing, and they proposed a new model, BKT. They use a handle marker to modeling the learning process. We know the deep learning is the area of deep learning. So the first deep learning based DKT model was being proposed in 2015. They will use RN to model the learning process and represent a change in the implemented layer, indicated a change in the knowledge state. Okay, now let me see the details about some models. Before I talk some model, let's try to define the KT task briefly. And basically, the task is giving the students interaction sequence. The sequence will contain the question and the set component associated with the question and the response. Our target is to predict attribute question Q star to predict the probability of the whether a student will answer this question correctly based on the student history interaction data. Okay, we can divide the model in 4 categories. The first one is deep sequential models. They will use deep sequential models such as the RNSTM to model the student learning process. And the second is the memory augmented KT model. They will use the actual memory to store the knowledge state, and then we will read and update this metric. And then is the graph-based KT model. They will use the graph nature of the graph to capture the connection of the different elements. The last one is the attention-based model. They will use the attention mechanism to capture the different information of the history. Okay, now I see the first category, the deep sequential model. We know the sequence is ordered by time, so we can use the sequential model such as TMRN to model that. The typical model are DKT and DKT plus and KQN. We'll talk more detail about the DKT because it is the first model used in deep learning. The input of the model is combine the knowledge component and the response. Here the example, suppose the C is equal to 5 and the one hot, the embedding of the C2 of the answer was wrong, we will concat one vector after this one hot embedding, and if the answer is correct, we will concat the embedding before it. Then we use we feed the X to the one sequential model, and we will get HT. Here we call that knowledge state. Then we use the MLP layer to get the finally probability. Okay, the secondary category is the membership agreement KT models. They will explicitly model by the actual memory, and the update is actually. We will talk more about the DKVMN. So the memory structure is use the key value pair, and the KMK store the conception representations, and the value MV will store and update the student's conception state. For input KT, the first step is addressing. It's very simple. We'll product with the MK and then use a augmented function to get the distribution of the probability. And then we will use the read process to make the prediction. Basically, this was the weighted sum of the MV, the weighted from the addressing, so we can get the RT. Then we concat the RT with the KT and use the connect layer to get the FT. So and another for connection layer to get the finally probability. About the updating the model, they use erase followed by add mechanism. So that means we will use the WT to decide how much information we will want to keep and how much information I want to forget. So that is some detail about DKVMN. Now let we see the next category, the graph, because we know the student and interaction can connect together, and the question and the cases also connect together. So we can contribute to a three-particle graph. And so we can use a graph-based technology to aggregate in such relationship. Such model and GKT and GIKT and SKT. So I will talk the GKT. This model reformulated the KT problem as a time series node level classification problem. The first step is aggregating. Such as there is a conception I, the aggregation will combining the knowledge stage with the neighborhood I and K and itself. Then use the update. Update will combine the graph structure and the embedding from the aggregating to update the hidden state. Then we get the HT to make the finally prediction. Okay, the next one is the attention-based model. They will use the attention mechanism and its variance to capture the dependence between interaction. And the first model uses attention. Here is SAKT. We know the attention needs three vectors. One is the query and the value and the key. So here is the value is from the question embedding, and the value and the key from interaction embedding. The difference in interaction embedding will combine the question embedding and the response. So the key value will contain the response information. Then I can use the multi-head attention to combine the history information. Then we can use the feed word network to get the finally probability. So far we talk some models, and I found there are some problems. The first one is the limited set information. That only use component ID and response, but ignore rich information. And that's only relied on the homogeneous question assumption. That means for a set of questions between two same cases, the contributor will be same the equal, but it is not really on the really word. The next one is about interpretable. We know that now the deep learning model and can make a remarkable process, but it is hard to tell how to do the prediction. It is not easy to interpret the result. Another one is lack of the standardization. Here the table, we can see the result of DKT are 9, the range from the 0.7 to the 0.8. It makes it harder way to research about the KT, because we cannot directly to compare different model. We have to implement all the model and run out in this set. Oh, the last one is overfitting. We can see the training and validation loss curve on the small data set. The training is always decrease, but in the validation data, we can see will achieve the loss very quickly, then get to raise. So about the 4 question, for the problem, there are the 4 challenges. The first one is how to capture more set information, and about overfitting is how to improve the generation less. About interpretability is how to leave the psychology theory, and the last one is how to evaluate in a standard prototype. Okay, now I will talk the recent events about how to solve these challenges. The first one is about add more information. So there are 2 categories. The first one is we can add more in the input, or we can add more tasks in the KT. So the AKT model, it try to add 2 information. The first one is the question information. Here is CT, the conception embedding, and they add the DCT. DCT is the variant in the question covered in the conception. And they also add a scalar difficulty of the question, so the input will contain the question and the conception info. And they also try to add the time info. They added the monitoring attention mechanism to the original attention, so the model will pay more attention on recent interactions. And about add more tasks, here our team proposed ATDKT. They try to add the question tagging prediction task and the individual privilege prediction task. The first one is we use the intermediate representation to predict whether the cases associated with a question at each time step. And that's one we will want to predict the individual privilege. Here the label is the correct rate from the moment t. Please note we don't use the KC level because the KC sequence is very short, so the result will not unreliable. About the next question, the solution we can add a psychology model to the KT. So our work, QIKT, to try to add some model in the KT. We all know that the student do the question, the equation different. So we use the K module to model the student learning after learning one question. And use the KS module to model the common knowledge state of a student. And when the student want to do a new question, the ability is different. So we add the PS model to model the student and do a specific question. And then we use the IRT prediction layer to combine the result to get a final result. About the evaluation, the answer is we can make a benchmark. So our team develop a Python library PIKT, and we report our result on the paper. In that paper, we want to answer 2 questions. The first one is what is the reasonable, reliable, and realistic evaluation process for the KT algorithm? We know the interaction is happening in the question, but the most model will build on the KC level, so they will expand the KC response data to get the KC level sequence. But there is some problem. We can see for the Q2, we can expand to the K2 and K4. But when we want to predict the K4, they can see the result for the K2. So that will cause label leaking. So one solution is we can aggregating the KC level back to the question level. So our team try use 4 different methods, and the results show we average the prediction probability of RKC is the best result. The next question is, how do different characters of student data and model design and prediction scenario affect the model performance? There are 2 different prediction scenarios. One is a one-step attention prediction. That means we all need to predict next one question. And the multi-step head prediction, we are to predict the multi-response. When we predict the future, if we use the predicted result, we see that it was accumulation. So our team implement the term model and run this model on 7 KT data set with 5 for the code validation. Here is our result. We found that the attention mechanism greatly affect the DKT model performance. And the DKT model, the first applied deep learning into the KT problem, is still superior. And we also found the choosing of accumulate or not accumulate prediction vastly influence the DKT performance in multi-step and prediction scenario. Also, we propose a new baseline simple KT. The model will use the difficult vector at the conception vector, and then we'll concatenate the question-centric evaluation. So the model can see the difference in the question between the same cases. Then we use the pure dot production attention to get finally HT. Our result shows that our model always rank as the top 3 in terms of AUC score and achieve the 47 win on the 12 model and based on the 7 public data sets. Oh, okay. Our toolkit is still developing, and this red test denotes that the new model as already said we add before our paper published. So now our toolkit have the 90 models and 30 data set per present code, and we read detailed documentation and easy to use. Here's some message from the GitHub. The one person said, your project had helped me tremendously in my research. Thank you very much. That is our goal to make this experience more easier. And our team also hosts a challenge. There are 100 participants from the different country, such as the NT Group, University, such as CMU and MIT, and welcome to use and contribute to our PIKT. Okay, the last one is about the generalization. So there are 2 methods. The first one is we can incorporate the advanced training into the KT. And the first, we will to train the model on the mini batch, and then we can get a normal loss. And then we will build the advanced example, and we will add some permutation to the input S to maximize the loss. And then we input this new X into the model so we can get the new loss. So the final loss will optimize together. Also, we can use the contract learning in the KT. The idea is we want to find the efficient embedding which to make the similar sequence together and the dissimilar sequence far away. So that paper proposes the 4 methods to build a similar sequence, such as you can use a question mask randomly to mask some questions ID or the inter-corp and the interaction permute and the question replacement. The last one is interesting. They will alter the question by their difficult. So if a user do the correct in the question, so they can replace the question to the more easy one. So the user can do it correct too. So if the user do the wrong in the question, they can change it to the more harder, so the student cannot do the correct on the question. Okay, so now we talk so many model and math. The last part will more relaxed. I will talk the applications and the future research direction. The first application is the recommend system. We know the KT is efficient to identify the user's strengths and weakness. So in the recommend their task, we can combine their interest and the knowledge state. So we can select this task not too hard or too easy for the user, and that make our system more engaged to the users. Knowledge state also important for recommending a learning path to satisfy the unique need of each learner. We call that was adapt learning. Here do an example to recommend the knowledge component D for the user. About the future research direction, the first one is about the setting for the answer we need to. The question we need to answer is how to collect and use more detailed multimodal dataset. The first one is the dataset. How we to collect the more dataset, such as response time and handwriting and other tracking on the student to the access. About the model is how to add this information to other models, such as the conception of the question. Okay, the next one is the interpretability. We can how to the combining the advance of psychology theory and machine learning for design more visible knowledge tracing models, such that we can use the memory theory and the learning theory. Okay, the last one is the both less learning data. Okay, in the early education, so you know, the data is from different school, but the different school, the conception and the learning in school is very different. So how to use, how to combine data together and do a better result on a smaller school. So there are two methods, the domain adaptation, or we can use self-super learning to solve this problem. Okay, that's all of my talk. Thank you, everyone.